Hi guys, I am Yashodhan Agnihotri, a final year student at IIIT Pune, and I will be your host for today. Welcome to our channel, Learn Competitive Programming with CodeChef. On this channel, we post weekly problem explanations and concept videos. Also, if you are interested in competitive programming and want to master data structures and algorithms, this is the place for you. So, what are you waiting for? Click on that subscribe button and kickstart your journey towards competitive programming today. The problem in discussion today is from the recent April Long challenge, and the problem name is worthy matrix. The difficulty level of this problem is easy and the prerequisites are binary search. Let us have a look at the problem statement. Chef found a matrix A with n rows and m columns. So where each row R and each column C, the cell in row R and column C is denoted by RC. It contains an integer ARC. So basically we have been given an integer matrix. So the matrix has two interesting properties. So the first, the integers in each row form a non-decreasing sequence for each valid I. This is the non-decreasing sequence, and the integers in each column also form a non-decreasing sequence. So the matrix is something like this. So 1, 2, 3, 2, 3, 4, 3, 4, 5. Yeah, so this is a worthy matrix. This is an example of a worthy matrix. Now, a k-worthy submatrix is a square submatrix of A, that is a submatrix with L rows and L columns. So it is a square, so it has L rows and L columns for any integer L such that the average of all these integers in the submatrix is greater than or equal to k. So basically, let us take the average of these four. So this is a submatrix, square submatrix. So the average of this is 2 plus 2, 4, 1, 8. So average is equal to 2. So now let's say we have k is equal to 2 over here. So this will be a k-worthy submatrix. So now what Chef has asked? Chef has asked us to find the number of k-worthy submatrix of the submatrices of the matrix A. So this is our problem statement. So first let us look at a sample case and then we'll proceed to the solution approach. Let us see the sample case. So here we have k is equal to 4 and we have a 3 cross 3 matrix containing elements 2, 2, 3, 3, 4, 5 and 4, 5, 5. So let us find the number of k-worthy submatrices. So let us first take this square matrix. So the average of this is, let's first find the sum. So 2 plus 2, 4, 8, 11. So 11 by 4, it is less than 4. So this is not a k-worthy submatrix. Same goes for this. If you calculate the sum, it is not greater than 16. It should be 16 or greater than 16 to have average greater than 4. So it is again not greater than 16. Now, if you take this submatrix, so this has sum is equal to 16. So 16 by 4 is equal to 4. So this is a k-worthy submatrix. Again, if you take only 4 as a square submatrix, it is again a k-worthy submatrix because its average is equal to 4, obviously. Same way, if you take only 5, it is again a k-worthy submatrix. So this and all the 5s basically. So we have 2 4s, we have 3 5s, and we have this submatrix which is 3 4 4 5. This is k-worthy, and we have also this submatrix which is 4 5 5 5. So all of these are k-worthy because their average is greater than k, which is 4. So the answer for this test case will be 7. As you can clearly see, 2 plus 3 plus 1 plus 1 is 7. So now I think you have understood the sample case. So keeping this in mind, let's go to the solution approach. So let us continue with the solution approach. So there are two parts to the solution approach. So first one is how to get the sum of any square submatrix so that we can calculate the average. And the second part is how to count the number of k-worthy submatrices. So let us start with the first part. So to find the sum of any square submatrix, what we do is first calculate a prefix submatrix. So let us see, we have the same matrix A that we had in the sample case. So what is the prefix submatrix? So prefix submatrix is take an element and the value of that element in the prefix submatrix, it will be the sum of, say we take this element. So the value of this in the prefix submatrix will be the sum of all the elements above it and to the left of it. So this element will be 2 plus 2 plus 3. That will be plus 4, obviously, the same element. So this will be the value of the prefix. Now let us calculate the prefix of this submatrix. So the first element will come as it is, as there are no elements above and to the left of it. This element, it will become 4 because 2 plus 2. Same way, this element, it will become 7. Now this element, it will become 5 because 2 plus 3, and this element, it will become 9 because 5 plus 4, simply summing the elements above it. Now this element, it will become 2 plus 2 plus 3 plus 4, which is 11. So this will be 11. Now let us see what will be this. It will be 2 plus 2 plus 3 plus 3 plus 4. So it is simply 11 plus I don't know, wait, 2, 4, so 7, 10 and 14 and 5. So the answer for this will be 19. Now let us go to the bottom row. First element we already have. Second element, it will be 2 plus 2 plus 3 plus 4 plus 4, 5 plus 5. So 4 plus 3, 7 plus 4, 11 plus 4, 15 and plus 5. So it will be 20. And the last element, it will be the sum of the whole submatrix. So it will be 33. So this is the prefix submatrix. Now let us see how we can get the sum of any square submatrix in the matrix. Now suppose we want the sum of this submatrix. So what we do is we take the prefix of the bottom right element. So the prefix of the bottom right element is 33. So 33 over here, now we need to subtract something from it. So we subtract, so the top right element, so we subtract the element just above it. So we subtract minus 7. Also we subtract the bottom left, which is minus 9. But what we did, what we achieved from this subtracting, from when we subtracted minus 7, we subtracted this row. And when we subtracted minus 9, we subtracted this row, right? But did you see that 2 got subtracted twice? Therefore, the element to the top left should be added once. So plus 2. So the sum of this submatrix, it will be 33 minus 7, which is 26, minus 9, it is 17 plus 2. So it will be 19. Now let us check if the sum is 19. So 5 plus 5 plus 5, 15 plus 4, it is 19. Yes. So the sum is 19. So using this technique, we can find the sum of any square submatrix. Now let us get to the second part as to how to count the number of k-worthy submatrices. So we move on to the next part of the problem where we count the number of k-worthy submatrices. Now before that, let us first define a square submatrix in terms of f of x comma y comma l. So what is x, y, l? So x comma y is the coordinates of its top left corner, right? And L is the length of the square submatrix. Okay, so now basically since we have x, y, l, so we can define any square submatrix in the form of these 3 parameters. Now let us see a very interesting property that will help us count the number of k-worthy submatrices. So here we have an example matrix A, and now what we have to do, we have to fix every element as the top left corner of any submatrix and then start counting. So let us fix 2 as the top left corner, and then we will start. So first we will keep L as the maximum length. So we will keep L is equal to 3 initially. Now the current submatrix that we have is 2, 4, 5, 688 and 789. So we are considering the whole submatrix. Now if you see, we need to calculate the smallest submatrix which starts at a particular index that has average greater than k. So let us see which is the smallest submatrix first. So if we start from 2, let us take 2. So 2 certainly has average less than 4. We have k is equal to 4 for this. So 2 certainly has average less than 4. Then we take this submatrix. So if you see this submatrix, it definitely has average greater than 4. So it is a k-worthy submatrix, right? K-worthy. Now, here is the interesting property. Now, since the array is increasing, it is non-decreasing along the rows and along the columns, therefore, what we can infer that if we find a k-worthy submatrix which has a corner at x comma y, then all submatrices with length greater than L will be k-worthy. So if this submatrix is k-worthy, then all submatrices which has their top left corner at x comma y will be k-worthy. So this submatrix, it will also be k-worthy, and this is easily observed by the fact that the values are increasing, non-decreasing along rows and columns. But how do we implement this? So let us try to see the time complexity analysis for this. So here we have first we will go to every element and we will set it as the top left corner. So that will be O of n into m, and plus we will have an additional factor that we will iterate over all the over the length of the matrix. So it will again be a minimum of n comma m. But if we want to optimize this further, we can apply binary search, and using binary search we can do it in less than this time. So this will be a greater time. So applying binary search on length. So if we apply binary search on length, we will get a better time complexity. Now let us see how can we apply binary search on the length of the square submatrix. So I will take the same square submatrix over here. So A is equal to 2, 4, 5, 6, 8, 8 and 7, 8, 9. So for binary search, what I will do first, I will set this as the top left corner, and this my L will be at 0 and my R will be at 3. Now if you see, what I will do is I will first take the mid is equal to L plus R plus 1 by 2, right? So since I have my mid, now I will take mid as the length of my square submatrix, and then I will calculate its average. So now if my mid, so if my average, it is less than k, so it is not a k-worthy submatrix, right? So then I will increment by L. So I will take L is equal to mid, else we will decrement our R and we will take R is equal to mid. So by this we are applying binary search on length, and you can easily see how it will work. And for the answer part, once we get a value of L which is final, so this is the minimum value of L for which any matrix whose top left corner is at x comma y is a k-worthy submatrix. So for the answer part, what we do is we get an L, where L is the smallest length for which matrix is k-worthy matrix, right? It is the smallest length. So what we had seen earlier, that for all matrices that have greater lengths than L and have their top left corner at x comma y, which is the top left corner of this matrix, all of them will be k-worthy. So how will we calculate the answer? So answer plus equal to, so we will just increment the answer which we had earlier. Now this will be the maximum possible length minus L. So this will be our increment to the answer. So say over here maximum possible length is 3 and we have our L is equal to 1 because up to this. So answer will get incremented by 2. Right. Now having seen this, let us have a quick glance at the pseudocode. So let us see the pseudocode. First we will take inputs. Next we will calculate the prefix sum matrix as we discussed. Then we will make a function to get the sum of a square submatrix. You saw we added the bottom right element in the prefix sum matrix, and we subtracted the top right and the bottom left elements only to add the top left element because it was getting subtracted twice, right? So then we will apply binary search on length by fixing every x comma y as the top left corner. So this is a O of n into m operation. So we will fix every index as the top left corner of a submatrix, and then we will check if it's k worthy. Now we will calculate the minimum length for which a submatrix whose top left corner is at x comma y is k worthy. So once we have the minimum length, now we can easily calculate the answer. So we add maximum length, possible length minus L to the answer. So let us see the C++ implementation for this problem. First, we will take inputs n, m, k. Here I've made a vector a. I've declared it globally so that I can use it in this function. So here I will take inputs, the matrix. Then I will calculate the prefix sums. If you see, I've just calculated the sums for the top and the left elements for every element, right? So we will calculate the prefix sums. Now, after we have calculated the prefix sums, what we do is we write this function which is getSum. So here the parameters are the coordinates of the top left corner and d. So d is the length of the square submatrix. So what we have done, we have written a of y2 x2, which is the bottom right corner, minus the bottom left and the top right, and we have added the top left corner because it was getting subtracted twice. Now coming over to the main part where we calculate the answer. First we initialize answer is equal to 0. Then we write two nested loops, and then we see what is the maximum possible length for the submatrix which has top corner at I comma j, right? So the maximum possible length, it will be n minus I plus 1 and m minus j plus 1. You can see this is very easy. So first we will fix L is equal to 0 and R is equal to maximum possible length, right? So L is our left hand side and R is our right hand side, and we calculate mid by L plus R plus 1 by 2. Now we check if K is greater than the average of the matrix. So here I have used the getSum function to get the average. So here mid is the length, right? As I told in the explanation, mid is the length of our submatrix. So here I've used the getSum function to get the sum of the submatrix and mid into mid. So mid into mid just gives us the number of elements in the submatrix. So this calculates the average of the submatrix. We check if it is greater than k. So if k is greater than the average, that is if the average is less than k, then we shift our left hand pointer to the mid, and else if it is a k worthy submatrix, then we just decrement our right hand pointer. So we equate R is equal to mid minus 1. Now once this is done, and once we have L greater than equal to R, we just come out of the while loop, and then we just add answer plus equal to maximum possible length minus L. So this L is our minimum L for which our matrix is a k worthy submatrix, right? So finally we just output our answer on a new line. I hope you understood the problem, and yeah, thank you.